Hello, this is Michael.
And this is Ryan, and our final project explores Schlieren imaging.
Have you ever noticed how on hot days it is possible to see mirages on the road? This is an effect of light interacting with air of different heat levels. We wanted to know if we can produce a similar effect in a lab.
Air of higher temperatures becomes less dense, which means light traveling through it interacts with less air molecules. This allows light to travel faster in hot air. Air of two temperatures can be defined by different indices of refraction, or ratio of speed of light in a vacuum to speed of light in the respective material.
As light moves from materials of different indices of refraction, its direction also changes slightly, as well as the optical path length changing. This is easily seen when putting a straw into a bottle and the straw appears to bend. The same occurrence can happen with hot and cool air, however the effect is much less observable.
How can we observe this phenomenon? In order to observe slight changes in speed and direction of light moving through hot and cool air, we must use an optical system which amplifies the effect of these changes. This system is known as Schlieren imaging, and our particular setup will use a concave mirror to focus light, a pinhole source, a camera, and a light block. In our case, we're using a razor blade, which is positioned at the focus point of the mirror, and it will block half of the light from reaching the camera.
So as the index of refraction varies at points in front of the mirror in our test area, the respective image points will change slightly at the light block. So it can either be obstructed more or obstructed less by our razor blade here, which will cut off 50% of the light. This will cause a variation in the amount of light that reaches the camera at each point, depending on the indices of refraction in the test area. This variation can be seen as variation in brightness, as captured by the camera. The Schlieren setup takes slight variations in the index of refraction and produces corresponding variations in image brightness. The effect that we see on the camera is called the Schlieren effect.
For our first test subject, we have a soldering iron, which we place in our test area, and the image that we see is the heat rising mainly from the tip of the soldering iron as expected.
We used another object that's hot, which was a ladle, and we placed it in the test area and then turned it on. And as you can see, it's very bright from the file. And even after we turned the ladle off, you could still see the heat rising from the tip.
Next, we tried a cold source, which is an ice pack, and what we saw on the camera is instead of a flow up of heat, we see a cold flow down.
So next we rubbed our hands together to create friction, which will increase the temperature of our hands. We then placed our hand in the test area, and we noticed that our setup is able to detect even these small changes in temperature.
So next we had our breath in the test area, and the camera shows a much more subtle change in index of refraction. We even noticed with nothing in the test area that we were able to observe just air currents from our room.
When we placed objects on the extreme temperature side of things, the Schlieren effect was much more noticeable with our setup.
Further applications include observing how sound waves change the index of refraction, and it also has many applications in aeronautical engineering, studying airflow of different vehicles as well as material testing.